Let's take a look at the following linear system. We have minus 2x plus 3y equals 7, and we have 5x plus 5y equals minus 5. Okay, so we want to find a lowest common multiple for one of the coefficients of one of our variables. We can actually look at the coefficients of x. We have minus 2 and plus 5 here. 2 and 5 have a common multiple of 10. So what we can do is we can multiply this first equation by 5, giving us a minus 10x, and we can multiply this equation by 2, giving us a positive 10x. So that way we can actually cancel those two terms in the next step. So let's go ahead and do that. We have 5 times minus 2x, which is minus 10x. 5 times 3y is 15y, and 5 times 7 gives us 35y, or excuse me, just 35. Now let's go ahead and write this product underneath so we can use elimination in the next step. So we have 5x times 2 is a positive 10x, and that'll actually cancel out very nicely. 5y times 2 is a positive 10y, and minus 5 times 2 is minus 10. Okay, so let's go ahead and combine these two equations. These two terms will cancel, so we have 25y. 35 minus 10 is 25. So we can divide both sides by 25. These two cancel, gives us y equals 1. So we have a nice round value for our y variable that we can plug into either equation, and we can get our value for our x variable. So let's go ahead and use this first one. We have minus 2x plus 3 times 1, or 1 is in for y, equals 7. And we want to go ahead and solve for x. This is going to be 3 times 1 is 3, so let's go ahead and subtract both sides by 3. That'll cancel. We just did 2 steps in 1 here. So we have minus 2x equals 7 minus 3 is 4. Let's go ahead and divide both sides by negative 2. That'll give us x equals 4 divided by negative 2 is just negative 2. And we have our value for x. So let's go ahead and write our exact solution. This was actually pretty simple because the numbers were nice. The solution point for this system is minus 2 and 1. This is the exact point in quadrant 2 where these two lines will intersect. So very useful to know that when we go to graph it. So let's look at another one. We have 7x minus 4y equals 12. And we have minus 5x minus 3y equals 8. So here is our linear system. So let's find a couple of coefficients who have a nice round common multiple. And we'll look at the coefficients of y here. We have a 4 and a 3. Those two are factors of the common multiple 12. But if you notice, they have the same signs. We need two coefficients with opposite signs, but that's actually no big deal here. It's nothing to write home about. We can actually divide one of the equations by a negative scalar. So if we, for instance, multiplied this equation by a minus 3, this would give us minus 3 and minus 4, a positive 12y. And we multiply this equation by 4, this will give us a negative 12y, which will both cancel very nicely in the next step. So let's go ahead and multiply this out. We have a minus 21x plus 12y equals minus 3 and 12 is minus 36. There's nothing wrong with multiplying by a negative scalar. It's just the same as we multiply by a positive scalar. So we manipulate it however we need to get the numbers and the equations to add up. All right, so let's write this product underneath. We have 4 times a minus 5x, which gives us a minus 20x. 4 times minus 3y is a minus 12y. And we have 4 times 8 is 32. So we can combine these two equations. These two terms will cancel, so that gives us a minus 41x equals minus 36 over 30, and plus 32 is a minus 4. Let's go ahead and divide both sides by a minus 41, which will isolate our variable x. These two terms will cancel. These two negatives will cancel. So we get x is equal to 4 over 41. All right, so we have a value for our variable x. Let's go ahead and plug it into one of the equations and get our value for our variable y. Let's go ahead and just plug it into equation 1 since we have a positive x out here. So we have 7 times 4 over 41, and we have minus 4y, y is what we want to solve for, equals 12. Let's go ahead and multiply this out. So we have 7 times 4 is 28 over 41 minus 4y equals 12. We want to move all the junk to the right, variable we want to keep on the left. So we subtract both sides by 28 over 41. Oh, excuse me, that's 41, not 91. Subtracting 28 over 41 on this side as well. These two terms will cancel, so we have minus 4y is equal to, we can write 12, we can convert that to a fraction of 492 over 41. Okay, so 492 over 41. Okay, that's correct. All right, we're subtracting 28 over 41. We have common denominators here, so we can combine these two in the next step. Minus 4y equals 492 minus 28 is, it looks like a 464 divided by 41. Let's go ahead and divide both sides by minus 4 to isolate and solve for a variable positive y. Let's turn this to a minus 4 over 1. These two terms will cancel. So y equals 464 over 41. We're going to flip the second and multiply. So multiplied by minus 1 over 4. And this will give us a positive, and a negative will give us a negative. And we have 116 over 41. Oh, excuse me. 116 over 41. There we go. And there's our value for our variable y. All we simply did was factor out a 4 out of both of these. This will give us a 116 over here. All right, so let's go ahead and write our exact solution for our system. Let's pick another color. Okay. So we have our x term is 4 over 41, and our y term is minus 116 over 41. Again, these numbers aren't always going to be pretty. In fact, they're usually not. But you can plug these two terms in for the respective x and y variables, and this will actually equal out, and so will this. You can check both of them. That's actually good practice. All right, let's squeeze in one more. We have 4x plus 5y equals 4, and minus 6x plus 4y equals minus 6. Okay, so here's our linear system, and we want to find a common multiple for one of the coefficients of a variable. And let's see, here we have, well, if we look at our y coefficients, we have 5 and 4, which is our factors of the common multiple 20. Only we're going to have to divide one, or we're going to multiply one of them by a negative scalar. So let's go ahead and multiply this first one by a positive 4, and this second one by a negative 5. That'll give us a positive 20y and a negative 20y over here, which will cancel in the next step. Let's multiply this out. So we have 16x plus 20y equals 16. And over here we have minus 5 and minus 6x is a positive 30x. We have a minus 20y. And we have a positive 30. So let's go ahead and combine these two fractions. These two terms will cancel. So we have 46x equals 16 and 30 is 46. So this will work out very nicely. These two terms will cancel, so we have x equals 1. And we like to see stuff like that because it makes our calculations much simpler. So we can plug it into either equation. Let's go ahead and plug it into the first one. We have 4 times 1, 1 is in for x, plus 5y equals 4. Let's do two steps here. 4 times 1 is 4, so let's go ahead and subtract 4 from both sides. These two terms cancel, and so do these, so we have 5y equals 0. And our y term is going to be 0. So let's go ahead and write our exact solution for this system of equations. It's going to be the point 1, 0. This is also called, as we saw earlier, the x-intercept, or wherever our y value is 0. This is where our line, or actually both of these lines, not only do they cross the x-axis at this point, but that's where they meet. So this is actually where they intersect on the x-axis. So this is very good practice. This is actually a very nice example here. They don't usually turn out this nice. So go over this one again, and in the next video we'll actually look at an application of solving these linear systems using elimination, where we multiply both equations that we find out from a word problem by a scalar. So I'll see you in the next video.